Okay. Hi, everybody. Today we are going to investigate two famous regressors which exist in SKLEARN. The first one is linear regression class, and the second one is SVR, support vector regression. Both of them exist in SKLEARN and find wide range of applications because they are very common and standard and could be used with linear or nonlinear regression tasks. First of all, we begin with the linear regression. We shall illustrate how it works through an example and by using a synthetic data set where we have two features, two input variables, and we have one target and the relation between them as should be is linear wise. We shall add to the synthetic data set a term of noise so as to give it the flavor of a real data set. And we can also show the performance accuracy of the linear regressor and how it depends on the level of that added noise. At the beginning, we import the necessary libraries here. So from the linear model, this is a submodel in SKLEARN, we import linear regression. Note how it is written with a big letter L and a big letter R. Each of them is capital. All other added things here, now we know. So we begin our work by creation of the data set. Because we are working with arrays and we shall select random values, we use NumPy random seed equal to 45. This guarantees that we get always the same random values when we run the program at any time. The number of samples in the data set is selected to be 150. Of course, it could be any number. The first feature here is equal to NumPy random rand integer, and the random values are selected between 500 and 2500 with the given number of samples. Note that SKLEARN works only with two-dimensional arrays. So we reshape this array to be two-dimensional by adding reshape between brackets -1 and 1. So this x1 now is the first feature or the first input variable. I have printed it to get an idea, to give you an idea about it. I am going to see only the first 4 elements from 0 to here they are, x1. These are the selected values. Okay. The other variable x2 also is created by using NumPy random round integer again with a range between 10 and 60, and it is also reshaped. Also, we have an idea about this. If you look at it, you will see that both of them, because they are reshaped, are two-dimensional, two brackets, as you see, at the beginning, at the end, at the beginning, and at the end. So both of them are two-dimensional, and the shape, as you see, of x is, for example, now x, we shall see that this array is created by concatenating x1 and x2, and it will have the shape of 150 because we have 150 samples, and it will have two columns, one representing x1 and the other column representing x2. So here we are combining both inputs, x1 and x2, by horizontally stacking them. In other words, we put them in one array beside each other in pi h stack x1 and x2, and we assign it to the variable x. So this x, as you have seen, is also a two-dimensional array with two columns. The first one represents x1 and the second one represents x2. I have printed x, the capital X here, to show you the first 4 rows and the first, because we have only 2 columns, the first 2 columns, 0 and 1. The 2 here is not shown in, because in Python, the third one, the last one, is not included. So here is x, here its shape, here is the first 4 elements. This is the first column with values taken from x1, and the second column with values taken here, 20, 52, 23, 10 from the second column. So this column and this column are shown here as features combined in one array. We combine them, as you remember, so that to have a regression process applied to x, and the effect here will be a combination of the effect of x1 and x2. So now we have created both variables. The target, which is the output here, the dependent variable, is linear. Here it is y, here is taken as x1 multiplied by a value plus x2 multiplied another value. So there is a linear combination between the inputs and the outputs. And we add to this linear combination, we add a term which includes some noise. And this noise has elements which are normally distributed with a mean value equal to 0 and a standard deviation equal to 15. And to have it two-dimensional, we reshape it again as you see here. So y also, which is the output, is shown to you here. It is also another two-dimensional array, and because it is a function of x1 and x2, so you have these elements. It is, as you see, two-dimensional also. Okay, now we have x1 and x2, we have combined them as x, and we have the output, which is y. And y, as you see, is linearly related to the x1 and x2. I have flattened x1 and x2 for use in the coming lines. I have also here used the flattened x1 and x2 in order to create a data frame, and this data frame will be used to find the correlation coefficients between x1 and x2. So firstly, I have flattened x1, I call it again x1, and I flattened x2 and call it again x2. And now here I created a data frame of x1 and x2, as you see here, and this is the target. If you print the total data frame df here, I am printing data frame head. If you keep the brackets here free without any value, it will give you the first 5 values always. So this is the data frame. This is the index. This is the first 5 indexes. First five values of x1, first 5 values of x2, and the first 5 values of y. So this is the data frame. And now when I apply the correlation function here, as you see, data frame dot correlation function, it gives you the correlation coefficients. I have printed this array core CORR, which is correlation, and you will find the values of the coefficients are given here. This is the x1, x2, and y. Here x1 and x2 and y. This is the setup which we have. Correlation between any variable with itself is 1. x1 with x1 gives 1. x2 with x2 gives 1. y with y, this is normal. Correlation, for example, between x1 and x2 is minus 0.121. The correlation is not that high. The correlation between x1 and y also is very small, minus 0.02. It is not that high. But if you consider the correlation, for example, between x2 and y, here x2, here is y, go down, it is 0.99, which means very high, about 1. You remember the correlation maybe from 0 to 1 or from 0 to minus 1. So it is very high positive correlation between x2 and y, and this gives an indication that the performance of the regressor will mostly depend on this relation on x2, and the role of x1 will be secondary. Okay, so now we have an idea also about the features and how they are related with each other, and the correlation between each of them relative to the other and relative to the target. After that, we usually split the data set which we have to two parts, one of them which is going to be used for training the model, and the other part which could be used to test the model for untrained values. So we have to import the function train test split function from SKLEARN. Here it is already imported from SKLEARN model selection. We imported train test split function. So this function exists. We can use it and pass to this function the arguments of interest here. We shall pass the X array, the Y, which is the target, this is the features, the size of the test part or test portion from the total will be 20%, and the other 80% will be used for training. And the random state is given a constant 42 as we did at the beginning. It is the same. So now, as a result of that, we have two data sets, X train and Y train, X test and Y test. Or in other words, X train, X test, Y train, Y test. Y test and X test and Y test will be around 20%. Usually this is a practical value, around 20, around 30, around 25. This is normal practice. The shape of the X test array, here I have just for you, I found it is about 30 as I remember. It depends on the number of the whole samples. If we have 150, so multiply it by .2, it will give you 30. So again, where it is, maybe, yes, here, it should be here. $100, no, it is not that. Here it is. X test shape is equal to 30, and 2 represents the dimensions. So 30 now, it comes as 0.2 multiplied by 150, it gives you 30 values or 30 samples. So this X test shape now is known to us. It gives some information about the values which we will work with. Now, the other step here, we need to initialize our regressor. We use the linear, it is already imported. We use the linear regression or regressor. These brackets means that we are calling this algorithm, and this algorithm is applied, and now the result is given in the model here. This is a variable called a model. This model now will be used to read the data set which is composed of X train and Y train. So model.fit, this function now needs to have the X train array and the Y train array. And after that, now the model has gained experience and can give us some specific information about the regression process. In order to check the accuracy and the performance of the model by using untrained values, we use the X test array, pass it to the predict function of the model. The result will be values which are predicted for each value of the X test. I have printed the first 7 values from 0 to 6, including 6, just to give you an idea about these values which are predicted by the linear regressor. To check the performance, we use 2 criteria, 2 testing scores here. One of them is the mean square error, which is already imported. Mean squared error is imported already. Here it is at the beginning. Mean squared error is imported, and R-squared score is also imported. As I told you previously, we have to use them both together because sometimes one of them, especially R-squared score, may not be sufficient to give a good picture about the work. So now we are here, we have imported the mean squared error and passed there the 2 arrays which are going to be compared with each other, which is the Y test array and the Y predicted array. And as a result, we will have the mean square error. And also we shall use both of them again and pass them to the R-squared score to find the value of R-squared. If we look at the values, here you will see that R-squared score is, as you see, 0.9999. It's about 1. This gives an impression that the work is done perfectly and the regressor is working without any problems. The mean square error value here is given 268. It is really acceptable. Really, the smallest or the smaller the value of MSE, the better the performance. But here, it is not that high. Really, it could be much more higher. So, principally, we have no problem with the performance of the system. And also, I have printed the output of the model, which is the coefficients of regression and the intercept value here. Because we have a linear regression, as you see here, we have the model coefficients, 1 for x1 and 1 for x2. And because these coefficients really, which relate the feature to the target, as you see, the number here, 50 for the first one, is very small relative to the coefficient of x2, which is about 20,000 against 50. This is again shows that the performance of the regressor heavily depends on the second feature, not on the first feature, and this is the value of the intercept as a linear regressor. Okay, so now we have all this information. Now another activity we are using. Suppose we have 2 values, x1 and x2. Suppose we have x1 equal to 2,500 and x2 equal to 3, and we want to find the output y for this value. This value must be presented as a two-dimensional array. So as you see here, we have 2 brackets, and we have created this array and assigned it values to a variable called new data. This new data now is passed to the model predict, and the model will predict the y value for this combination of x1 and x2 and gives us the output. If we suppose, for example, that we are working to estimate the cost of a house where, for example, 2,500 is the area and 3 are the number of the rooms, for example, or bedrooms. So for this x1 and x2, the output predicted price, for example, will be presented as the value of y. Here, in this case, for these values, it was found about 185. 185. This is not that important. So we have tested the regressor by using the X-test. We have tested again by using other values here, and it gives us acceptable results. Now we want to show the scatter plot, which represents the data set and the predicted values. So I have drawn here two scatter plots. One scatter plot with X-test for, as you see here, the second feature, all rows. Here the index 1, the second feature, and this is the test, and the y-test. So this is the original values, y-test and x-test, and I have given them the color red. The predicted values also for x-test, for the same x-test here, are given a color black. Now, if you look at the scatter plot of, I have given a size for the dots here of the red, as you see, 55, the red of the black, which is 25, to show so that you can see them. So if we look at them, we see really the red dots are enclosing the black dots, which means they are not displaced far from them, which means that they are practically the same, and this means that the regression process is very highly accurate, very accurate work. The two data sets are overlaid on each other, and there is no displacements, no distances between the points, which means that everything is very nice and it works nice. Okay. Support, we want to show the predicted values, which are points which are represented by X-test and Y-pred as a curve, and to connect between all the points here. For this purpose, I have now to include this piece of code to show that. I shall take away this hash sign and this hash sign. No, the first one must be kept. This is not in the program. This is just an illustration. And I shall take this one away. And now what we have. Before explaining to you about these two lines of code, for visualizing regression curves, you must sort your inputs, which means you have to arrange them to be in an ascending or descending order before plotting. After arranging this sorting of the X values, you can carry out the prediction over them. And then you can plot the line or the curve which connects between or describes the relation between sorted X values and the predicted values of these sorted values. So in order to sort the values, firstly, we use the NumPy argsort function. We pass there the values which we want. Here we will pass there all the raw values for the second column, 0, 1, 1, here it is. And here now we shall have, as a result of that, an array which includes the sorted indices of all the values. So what we have done here, we have extracted the entire second feature column. This is the word entire, all the rows. This is the second feature from X test data. And now we have figured out the order of indices in an ascending manner and stored these indices in the variable called sorted indices. Now we shall use the sorted indices to plot the curve. So we use PLT plot function. We pass there the X firstly, so X test of sorted indices only for the second feature. This is the X values. And now the predicted values, Y predicted for the sorted indices, and I given it a color green. Now if we run the program, something wrong is there. And line 110, so and so, based on, let me see. Yes, here there is no prime. As you see here, there is a prime. Here there should be a prime. If I run it now, again, no? The prime should be outside, as I noticed, maybe here. Now, if I go back, yes, let us run. It is already run. You see how, because the dot, the black one represents the points, they are connected continuously with each other to show the curve resulting as a result of sorting the X test values. But this doesn't show you the regression line relative to the prediction line, to the predicted values. Here we have two variables or two features, X1 and X2. Here we can find the regression plane with X1 and X2 as axes, and the Z value will represent the prediction. Or more simply, we can use only one feature as the X values, and the ordinate or the Y values will be the predicted values. I tried here to show you the second case. So as you see here, this is the scatter plot of the data set which we have, and this is the regression line, as you see, with the intercept around dot 8, or maybe dot 8, maybe a little bit higher. Okay, how we did that? I did it separately so that you can see it. So again, I have imported all the required libraries. This is normal. I have again created the data set as I did before and combined the variables together. And then I have defined the relationship between the target y and x1 and x2 here. And I have called the regressor. Everything is this is a repetition. But in order to plot the regression line here, we need to consider one of the features equal to 0 or not existing. A common practice also is to consider the second feature as a fixed value and to work with this fixed value with the x1. This fixed value is not selected randomly. It is selected as the mean value of this feature. So we call from NumPy the mean function of x. X here is the combined, you remember, array of x1 and x2. If you put the index 1 here, you mean the second feature. So we find the mean value of the second feature and assign it to a variable called x2 fixed. So x2 fixed is the value which represents the mean of the second feature. If you want to have an idea how much it is also, this is x1, x2. Here it is x2 fixed, which is the mean value, 38.88. This is the mean value of the second feature. This value will be used as a constant and it will not change. For the second feature, we use only a constant value. Okay, so we are here. We have used x2 fixed as a constant value representing the second feature, and the first feature will be as an array with the different values. In order to plot the regression function, we need to create a range for feature x1. Here we use NumPy linspace. We took the same values as before, between 500 and 2,500. The number of samples, as usual, 150. We took it, we reshaped it. We get a value, an array x1 range here. It is called x1 range. And I have shown you also the first 5 rows of this range. Who wants to see them? They are given down. And after that, now, we shall create a column with the inputs which we have, which is x1 and x2, but x2 constant and x1 is the array. So for this purpose, we use a function in NumPy called NumPy full-like function. We shall create now an array of 2 columns by using NumPy horizontal stack The first column is the values of the created X1 range. And the second column really is which results by using X2 fixed, which is the mean value, which we have calculated, with the array of the same size and the same type of X1 range. So this X1 range just indicates the type of the array in which we will have X2. So if you go to X curve, the resulting array here, it will be two columns, one of them exactly X1 range, and the second one will be the constant value which we have seen. So if we look at them here, sorry, yes, here it is. So this is the first column, which is X1, and this is the X2 constant, so the mean values. Now this is the values of X. For these values now, we can find our predictions. So now we take the model. We have already imported the model. Here it is, and applied it to the XY, and now it is ready for use. We now use the model, call the prediction function, and pass to the prediction function the values of X curve. Now we get the Y predict values. With these values now, we can print the regression line. So at first we plot PLT scatter, the scatter plot, PLT scatter of X and Y. This is the X input, this is the Y, this is the data set which we have. We gave it a color blue. These are the dots which are the resulting scatter plot. And now we plot the line, PLT plot the line with the input X1 range and the output Y predict, which was predicted. And we gave it a color code, a color equal red. Now with this, we shall have this picture, as you have seen, which represents the overlay of the regression line over the scatter plot. Well, now let us see also one interesting thing. I hope that we can demonstrate it to you. If we go back here, yes, here is our Y, the target Y, where it is. Here it is Y. And you remember we have added a term here with values representing a normally distributed noise. Let us take away the noise and consider how this affects the accuracy of the regressor. Let us, before this plus here, I will fix a hash sign. Now all the values behind it will not be included in the program. And if I go down and look at the R squared, remember, 0.9999, it's very high. Indeed, it's very high. And MSE is 238. Now, if I run the program, maybe this will be approximated to 1. It will be more accurate because we are not including the noise. And this, as I expect, must become smaller. Let us run it and see what will happen. If we run it now, yes, as I expected. So look, R squared score is 1. The MSE now is equal to, again, 0, about 0. So the mean square error is 0. So practically there is no error. Let us put another value. Let us play with the value of the standard deviation there. Okay, it was given here 15. Let me put it instead of 15, 2 or 3, for example. And now I shall include this portion. I shall take away the hash and go back and run the program. Remember, this was about 0.999, and this was about 200 and so about 230, like that. Now, if I run it again, I shall have a value, of course, higher than 0 here. But, and this also will become less than 1, but the value here will be, it seems to me, it will be much smaller than 200. Let us run it and see. Yes, this is, again, 0.9999. This is 8.6, which is very close to 0, but it is not 200. This gives you an answer that the performance of the linear regressor is affected by the outliers and by the noise, the level of the noise. This issue will be treated by us in the coming lectures in order to improve the performance of the linear regressor or linear regression function. We have in SKLEARN another regressor called Reg, linear regressor, where it also improves the performance because of the existence of outliers. And in the next example, which I will discuss with you also, we shall use the second type of SKLEARN regressors, which is the SVR, support vector regressor or regression. This is a class taken from the support vector machine submodule. And this SVR includes also hyper parameters, which are used to tune the performance of the regressor and to minimize the overfitting and associated deflections. Well, I keep this for the next lecture, where we shall discuss with you in detail how the SVR works, its kernels, and its hyperparameters, and its performance in general. With this, I finish this lecture. Thank you very much. See you in the coming lecture.